Navigation, now let's sort of give ourselves a definition of it. I think of navigation as planning and executing travel from one point, presumably where we're starting, to a second point where we want to get to. It's both planning it and then executing it. Are we there yet? So there's two parts of it. It could be on the surface of the Earth, in the air, in an airplane or a hot air balloon, or in space, or whatever, on the sea or under the sea. And there are two broad classes of navigation systems. There's one which once was considered the high-tech system. The promoters would tell you it's better than any other one, and that's the INS, or inertial navigation system. An INS system does not use external reference points. It requires you to know where you started, what your orientation is, what your initial velocity was, what your in all three dimensions of space, and what your initial angular velocity was. Were you rotating about some axis or not? And if so, what axis and how fast? Okay, so that you need to know. Then you need to continuously measure your instantaneous acceleration in all three spatial dimensions, and also your angular acceleration. How fast is your rotation rate changing? So 6 things you need to measure, but you can measure all 6 of those without any reference to the outside world. Physics says you can do that, and you can do that. The only question is, how precisely do you do it? How much money do you spend on it, and so forth? You also need a clock, or what we say in navigation, a chronometer, an accurate clock. So if you know where you started and what your initial conditions were, you don't have to look out the window, and you can tell where you are, where you've gotten, etc. That's INS, inertial navigation. The other class doesn't have a fancy or common name. I'm going to call it external reference-based systems. Here you need to know a set of reference points. You've got to know where they are. They could be trees, rocks, whatever. Presumably that's what cave people used, and we still use that too. You need to determine your position with respect to those reference points during the process of navigation, and you can do that by measuring distances if you have a rangefinder. More commonly, you measure angles. Celestial navigation is strictly by angles. The traditional way of navigation, boats, sailing, is you measure angles, bearings to points on the shore or whatever. And you don't have to, but it's typically you use a chronometer as well. Human beings, animals, GPS use the external reference points. It's true we can stumble out of bed, walk down the hall with our eyes closed and whatnot, probably make the right turn into the bathroom, but I think we're not really doing inertial navigation. We're just feeling the rug or whatever. Ballistic missiles, especially the long-range ones, use exclusively inertial systems, and that's where the great investment of money was spent in developing such systems. The people at the Charles Stark at Drake Laboratory, formerly part of MIT, used to argue that's the only way to do it. Well, do it well. It turns out they oversold that. They're wrong. There are other ways to do it. The important point isn't that one way is better than the other. In fact, what's clear already, and people didn't have strong biases, knew this long ago, is that using the two things together is the best way. There's a fantastic synergy, which I don't have time to go into here today, which when you use both systems, the weaknesses of one are the strengths of the other. So using them together is the best thing. GPS has certain problems. An inertial system could fill in for those. And so the systems of the future will be combined, and aircraft already use combined systems, and automobiles and mountaineers and whatnot who are using GPS will presumably be using an inertial supplement as well. You don't have to do everything one way, and doing things two different ways is often the best way. Brief history of the GPS system. The use of radio waves for navigation began in the 20s. It was used extensively in World War II. In the late 50s, early 60s, the Navy and the Air Force separately wanted to have global, 24-hour, all-weather, highly precise navigation systems for their ships, their planes, and ultimately for their missiles. The Navy had one system actually deployed called Transit, had 7 satellites, very simple way, not terribly useful, but better than nothing. They experimented with another system called timation, putting highly accurate clocks in space, and the Air Force had its system called 621B. They used to number systems by strange ways. The Department of Defense established a joint program, and joint means all services, in 73 and put the Air Force as the lead agency for that. Although there are a lot of technological challenges, it turned out the bureaucratic ones were the greatest challenges that had to be overcome. There were a couple of years in which the Air Force, the lead agency, asked for $0 in their budget for this. And no one wanted to pay for it because it would have a lot of benefits for other people. It just had no real proponent except the civilian leadership in the military and the scientific leadership at the military laboratories, and they prevailed in the long run. And the real system development began in '79. There was the famous incident in which the Soviets shot down Korean Airlines commercial flight 007, which had strayed off course. The pilots, the navigator, put the wrong inertial coordinates in the INS unit. It was shot down, loss of life of all those aboard over Sakhalin Island. And after that, right after that, President Reagan said the GPS system then underdeveloped would, at least parts of it, would be made available for commercial aviation to prevent such an accident from ever happening again. The GPS system had 16 satellites up during the Gulf War, and it was used extensively and got a lot of publicity through that. And the system finally came into operation in 1994, and it's there now in full operation. And the use of it is growing extremely rapidly. You know, I spent $300 here, and I bought into a system which has had about $10 billion now invested in it. And you can do the same thing. If you wait a couple of years, it'll be $150 maybe. All of you, within 10 years, will be using equipment which makes use of the GPS system, whether it's conscious or unconscious. Half of you, at least, will be making use of it in one way or another in less than, well, probably within the next 5 years. No one ever planned for what's happening and the fact that this incredibly useful system. It's a marvelous story of discoveries in basic science being applied to a particular problem, which turns out to solve a wide class of problems, having a utility much greater than anyone ever dreamed. So the commercial end of the business is dominating already the military use of it, and it's escalating at a rate that's just extraordinary. The complete GPS system, which is up there now, has 21 satellites plus 3 spares. That's 24 total. Each one carries 4 very precise clocks, atomic clocks, which I won't explain in detail, but the key thing of the clocks is they're a frequency standard or a time standard transition between 2 levels of the cesium atom or the rubidium atom. There are 2 cesium clocks and 2 rubidium clocks, only one of which is operating at a given time. It's not that they vote. The other ones are there just in case the clock fails, because without the clock, the system is useless, and the satellite's designed for 7.5 to 10-year lifetimes. One of the great achievements was packaging atomic clocks. The original ones were the size of probably a dorm room or a bedroom or whatnot into something small enough to be on a satellite and be unattended for a decade, a non-trivial achievement. It's important that the clocks in all the satellites are well synchronized, very well synchronized. If you come here and study physics, you'll learn when you study relativity that synchronizing clocks at different places is a tricky operation. Much of Einstein's discussion in his early presentations of relativity involves synchronizing clocks at different places and so forth, and it gets even trickier with general relativity. But it must be done, and it is done. These satellites continuously emit a time-stamped radio frequency signal, stamped precisely in time because of the reference clock on board. And the constellation of satellites is chosen such that at any point in the Earth, at all times, there are at least 5 in view. In fact, in view with at least 5 degrees above the horizon. The basic way the system works is by measuring the time of the distance. The user measures his or her distance from the satellite by measuring the signal travel time. So it's signal travel time, and the signal is a radio frequency wave traveling in vacuum at the speed of light. So that's the first thing to keep in mind. You're measuring travel time. I think people in the investment world say time is money, but we're scientists, engineers, technical people. For us, time is distance. Okay. That's the way you want to think about time. Now, there's a concept used in this business called pseudo-range, and I need to explain that to you. It's a key thing. Suppose the satellite clock is perfect. Not true, but suppose that. You're the user. You have a clock, but it's out of synchronization by some amount delta t. And you don't know how much it's out of synchronization, because if you knew, you'd just reset the clock and it would be synchronized. The satellite is here at some known position, x1, y1, z1 in three-dimensional space, and emits a coded signal timestamp t1. It might be 131.00 something. Okay, it emits it, radio waves go in all directions, and you are the receiver on the Earth or above the Earth or something. At some position you'd like to know with respect to the same coordinate system that's used here, x, y, z, and you receive this signal at time t1 prime, somewhat time later. Okay? You, of course, know where you are, but you don't know where that is with respect to the coordinate system used here, so you're trying to find out that distance. The true range we call R1, and in three dimensions, that's the sum of the squares of the differences of the x, y, and z coordinates. The first two terms would be the case in two dimensions. That would be a right triangle. Okay. Well, that's the velocity of light times the time at which it was received corrected for the clock error. So delta t, when added to this, gives me the correct time synchronized to this clock. So here's the time the clock reads the synchronization error, which I don't know. But if I knew it, I'd add it here, subtract the time of emission. That would be the true time it took the radio frequency or light signal, whatever, to go from here to there. And that would give you the range. You wouldn't know the separate coordinates, but you know this combination. If you calculate it without knowing this correction, using the time your clock reads and the time that was stamped on the signal, you call that the pseudo-range. So it differs from the true range by some amount delta r, which depends on how much the clock error is. And that's just c times delta t. C is a very well-known number, very close to 3 times 10 to the 8th meters per second. And a meter is a yard, plus a little bit. So pseudo-range is a range measured by the time difference of arrival of a light or a radio frequency signal, but with clocks which are not synchronized. Okay, if you think about it, one measurement. Let's, for the moment, forget about the error in the clock. One measurement places you, one measurement of the pseudo-range, somewhere on a sphere of radius r about the satellite. So if you imagine you're at the center of the sphere, the satellite's at the center of the sphere, you know that you're on a sphere of a given radius, r1, actually r1 prime, somewhere on this, but you don't know where. You just have that one measurement. Okay. Suppose you make a similar measurement of another pseudo-range from another satellite at another known location. That's R2. Well, the actual range you'd use the same, if you knew it, you'd use the same correction, because this delta t is due to your clock, not the satellite clock. The best you can do, though, is use what your clock says, what the satellite signal was stamped, and you could pseudo-range R2 prime. Now, if there was not an error, if you knew the true ranges here, these two spheres would intersect on some, in 3 dimensions, intersect on some circle. So here's the first sphere. You know you're on it somewhere. You know you're on this sphere. And now 2 spheres intersect at a circle. I'm cheating with this Nerf ball, but you get the idea. The Nerf ball is supposed to be penetrating the basketball. So you know you're somewhere on that circle. It's a little easy to see this in here and look just at the solid lines. So here's the radius of the pseudo radius that we're from this satellite. It's the circle part of it shown here. We know we have a measured pseudo range from this satellite. That's the heavy blue line, and they intersect at 2 points. Okay, the circle collapses to the 2 points. Okay, well, they intersect here and they intersect here. The problem isn't the 2 points. Usually one of these is unphysical. It's in the middle of the Earth or it's way out in space and you know they're not there. So it's not that I don't know which one of these to pick. It's that I know, because my clock isn't well synchronized, I know that I could be anywhere between here and here, and I could be anywhere between the solid blue line and the light blue line. And of course, it could have the other error. It could be on the other side. So there's really a third line here on either side of the solid lines. Well, how do we deal with that problem? Well, the way the GPS system deals with that problem is that you use a third satellite at another known location, the green one. So you measure the pseudo range here, a solid green line. Okay. It intersects at 2 points here. It intersects up here at 2 points. So I got 1, 2, 3, 4, 5, 6 intersections, and none of them are right because of my clock error. But it's the same clock error. There's one delta t. It's my clock that's at fault. So I just start adjusting it by trial and error. And there's one value of delta t which brings this into a triple coincidence right here. And there might be one somewhere else. I guess in this case there isn't. And so that's the right answer. So by using 3 satellites, you can solve for delta t as well as the location. Now, that's in 2-dimensional space. It's pretty obvious what you have to do in 3D, and that's use 4 satellites. Because if you have 3 satellites, no matter whether the actual ranges or the pseudo ranges are used, they will intersect at actually 2 points somewhere. But it'll be the wrong 2 points. By using 4 satellites, you'll have this 3 times, and then by adjusting the delta t, which you don't know, you can bring the intersection points into coincidence. So 4 satellites are required, and when you get the right delta t, you achieve what's shown in this slide here, and I have to turn some lights out to make it visible. This colored picture, by the way, and the previous one are taken from the Scientific American article, which is mentioned in the reference page at the end of my notes. You see here that here is satellite 1, 2, and 3. And this picture is drawn for the case where delta t is 0. So imagine you've used the 4 satellite, you determine delta t, you now just draw the picture. The 3 spheres intersect at this point here and another point which you can't see behind it. But that's the basic idea. They couldn't draw 4 spheres even at the Scientific American and make it legible. Whoops. Get it right here. Okay. So I've said everything but what's on the bottom here. So let's just repeat that. Okay, now back to 3D. If you've got non-zero clock synchronization error, you'll have 4 3-fold intersections rather than 1 4-fold intersection. By adjusting delta t, by figuring out what delta t does it, you'll achieve a unique 4-fold intersection of the 4 spheres. And I've already illustrated that in 2D. And so in that way, you learn from 4 measurements, you learn 4 things, and you should from 4 independent measurements. You learn your x, your y, your z, and the clock error. So now you've got a clock that's as good as the atomic clocks up in the satellites at the price of your $30 wristwatch. The receivers, GPS receivers, mine included, have clocks that are no better than the clock on my wristwatch here. Don't have to be fancy. They can't be terrible, or it would take a long time to find out the right adjustment. Okay. So let me just summarize that. . summarize the basic principles we've been describing. And if all you carry away from this talk today is what's on this slide, I'll be happy. This is the most important thing that I want you to understand. And it's not difficult to understand. Okay, the GPS works by measuring 4 time differences of arrival. The clocks in the satellite must be synchronized very well. The speed of light, 3 times 10 to the 8 meters per second, if you think of a meter as a foot, that corresponds to, a meter is 3 feet as a yard. That corresponds to the statement that in 1 nanosecond, 10 to the minus 9 seconds, 1/1000th of a second, light travels 1 foot. So when people are making delay lines, they think a foot per nanosecond. So the GPS system does synchronization not to 1 nanosecond, but a few nanoseconds. The GPS engineers worry about nanoseconds. A few nanoseconds is important to them. That's a lot of time for them. So they have to synchronize very well the clocks in these satellites. The user's clock doesn't have to be synchronized anywhere near that well. They can lose a second a day, say. The satellite positions have to be very well known, because each foot of satellites out of the way is a nanosecond of travel time, and a few hundred nanoseconds, can add up to serious error. Okay. Now, sometimes you have additional information. You know you're at sea level because you're in a boat in the ocean. So you don't have to solve for your altitude. You could use that as an input parameter. You could get by with 1 less satellite, or you can use that to improve the accuracy of your solution. So 2D navigation with known altitude or whatever is more precise than 3D. Now, there's one thing which I have to fess up to. I won't go into much detail here. Is everything I've said so far is C is constant. It's the velocity of light, speed of light, radio waves in vacuum. That's true, that's a constant. But the radio waves that get to us from the satellites up there go through the upper, something called the ionosphere, which is way up here, where we have charged particles, electrons, which cause significant effects on the speed at which the radio waves propagate. And then when they down to the lower part of the atmosphere, called the troposphere, they're also affected in the more dense part of the atmosphere. So the system has to make corrections for both of those, and those are tricky corrections to make, but and that's one of the limits to accuracy, but it's done. Okay, so there's the heart and soul, the idea of the GPS system. The rest is details how you build the equipment that does this job. Okay, now it's time for the first pop quiz. It's pretty obvious to you that if all the satellites are very close together up there, that's not going to be good geometry for measuring time differences of arrival, because the time differences will be very small, and so you'll be working with numbers that are almost equal, trying to figure out where you are. And you move around, those differences won't change much if the objects, the satellites, the 4 satellites are all close together. So the quiz is the following question. What is the optimal geometry or range of where would you like to have the 4 satellites in order to give you the most accuracy? Because all together doesn't work. If you put them all 4 on top of one another, that's obviously no good at all. So how should they be arranged? So let me give you a couple minutes, think about it, talk to your neighbor. You two should talk here, but don't speak too loudly. If the person on your right side doesn't have a good idea, talk to the person on your left side or behind you. And one clue, the radio frequency waves do not go through the Earth. And if the satellites aren't within view, straight line view, they can't help you. Any questions about the quiz? Put up your hand when you think you have an answer, and when I see there's a consensus developing, I see one hand. Someone else must have an opinion. Be bold. Make a guess. Another hand. I have to at least one more hand here so we can compare answers. I will call upon, but you two are sitting next together. I'm going to call you a group because she told you the answer. Okay, I'll call on someone. Let's see. Okay, you're going to volunteer? Okay, so one of you two report first. Stand up so we can hear you, and you're sort of in the middle, but look around as you're talking. Go ahead.
It would be a tetrahedron.
A tetrahedron. Yeah. Okay, so if we're here, where are the corners?
They're all equal distance from each other
As far as from the right. So one is straight up ahead.
And then there are three.
One there, 120 degrees, another 100 degrees. So the four make a tetrahedron. Okay, that's an interesting thought. What do you say? Pardon? Okay, that would be the right answer if the Earth didn't get in the way. But if you're at the center of that tetrahedron, is what you're asking to be, then you can't see the other three because the straight line to them from you is passing through the Earth. So out of the possible 25 points for each correct answer, you get 25, or the possible 100 points for the whole answer, you got only 25 points. But you're very close, so actually I give you 50 or 60%. What you do is just bring those points up to the horizon. So one overhead and three on the horizon, separated by 120 degrees, and actually you need them about a few degrees above the horizon in order that the atmospheric propagation effects are not overwhelming. So very good, good work. And the rest of you may or may not have figured it out. If all together is bad, then somehow you want to get them as far apart as possible, and I'm guessing that's what you were thinking. Okay. So that's the most important part of the lecture. You could go home now, but I hope you don't, okay, because there's a lot of fun coming. The GPS system is divided into three components. The space component, which consists of the 24 satellites. The user, that's me, that's you, at sea, in the air, could be some satellites in low Earth orbit, could be military vehicles, could be your delivery van, whatever. And then there's a ground control element. There are 5 or 6 monitoring stations around the world. There's a master station in Colorado Springs, Consolidated Space Operations Center, and there are ground antennas. You, the user, receive. You don't do any broadcasting. It just comes down from the heavens to you, and you don't have to send anything anywhere, and you don't. Okay. The ground control receives information from these satellites. In fact, checks on them, measures their positions, their degree to which their clocks stay synchronized, etc., and it broadcasts up, sends up information asking us, making adjustments in the satellite, and sometimes even correcting the orbits. So there's a lot of talk back and forth here. A lot of the stuff now done on the ground, and as this GPS system is maturing, is being done in space because the satellites just talk to one another. They can talk to one another and synchronize their clocks. They don't need the ground, really, but there's I will mention later that you can never get rid of stations on the ground and how that comes about. Now, the 24 satellites are arranged in a constellation which consists of 6 planes, each containing 4 satellites. Now, all the books say they're in 12-hour circular orbits, so it takes 12 hours for the satellites to go around their orbits one time. I've got a scale model of that here. Here's the Earth, which, as you know, rotates about a certain axis, which is almost fixed in space, for our purposes fixed in space. This wire represents one plane of the GPS constellation with 1, 2, 3, 4 satellites. Okay, the Earth rotates once a day. This plane stays fixed A lot of people think the plane's going to rotate with the Earth. Not so. The Earth rotates. This plane is fixed in space. The satellites rotate around it. I can't demonstrate that, but these 4 satellites rotate around, and in 12 hours, satellite number 1 is back to where it was. So while they're rotating around, the Earth is rotating. The Earth rotates once every 24 hours, the satellite's 12 hours. So you see the same satellite every 24 hours. 12 hours later, it's back to where it was, but you're on the other side of the Earth, you can't see it. There are 5 more planes like this arranged around, and an important quantity is the so-called angle of inclination. Let's see, I guess I want to do it this way. Measured with the equatorial plane of the Earth. So think of a plane that goes through the Earth's equator. Measure the angle that the plane makes with respect to the equatorial plane. The GPS system uses 55 degrees. So there's 5 more planes at 55 degrees. This is quite a lot of satellites, and they're spaced around this way uniformly. Okay, so that's the GPS constellation. On the scale of that model there, the satellite orbit radius is around 4.2 times the radius of the Earth. This sun would be 2 miles away, so it'd be way over in Champaign somewhere. Okay, so this part's the scale, that's not. All the while the satellites are going around here, their solar panels, which I'll show you in a minute, are rotating so they're always at right angle to the sun. That doesn't happen automatically, because if I don't do anything, as this satellite goes around, actually, this depends on this plane to be okay, but if we had this situation here, we'd have to make adjustments to the angle there. When you're up here, you'd have to make certain adjustments. The satellites also keep their antennas pointed towards the Earth, and they bathe the entire Earth, actually 40% of it, with the radio waves. They don't bother putting stuff way out here in space where there's no one using the system. So these do a dance, keeping their radio antennas pointed to the Earth, their solar panels towards the sun, all the while going around. Okay. The ground tracks repeat actually not every 24 hours, but 23 hours and 56 minutes. The reason is the period is actually 2 minutes less than 12 hours. And the reason for that is that the Earth makes 1 more rotation when it goes around the sun each year than the number of days in the year, which on average is 365 and a quarter. So when the Earth is rotated once from the point of view of someone looking outside the system, the angle to the sun is not the same. It has to make an additional 1 over 365 rotation before we have 1 solar day completed. And so the length of the time it takes the Earth to return to its original position is, with respect to external reference frame, is 23 hours, 56 minutes. It takes another 4 minutes for the additional rotation of the Earth to bring the sun back to the same position. The sidereal day is 23 hours, 56 minutes. The solar day is 24 hours. The satellites are chosen such that in exactly this amount of time, they're right back to where they were before. The reason they did that, among other things, was that in the original test program, they had only a few satellites up there, and they wanted to have them come back at convenient times of the day, not have to do tests at night and so forth. So it was convenient to have the few satellites come back to the same configurations, except for 4 minutes, basically at the same time, in the same place. It turns out in the long run that's been a unfortunate choice, because the satellites, because they're going over the same ground tracks, every second orbits over the same part of the Earth, they pick up this, they are affected by the same gravitational anomalies, Professor Chen's mountains and all that kind of stuff, and these satellites tend to bunch up, so they have to use rocket fuel to keep them spaced apart. If they had picked anything other than that number, the random process would have taken care of the averaging out those gravitational effects due to the fact the Earth is not a perfect sphere. Now, I've got a short videotape, which I will try to show here, which is taken out of a clip from a manufacturer of one of the commercial GPS units, and they had about 30 seconds of total useful material for my purposes in it. And if everything works well, you'll see it up there. This was the lead into the this shows you the satellite. For some reason, it starts off with the satellite backing away from you. I guess you've just launched it from the space shuttle, although these satellites are not launched from the space shuttle. And then you see it coming at you. You see its solar panels, and the things on the front end of that are the radio antennas pointing towards the Earth, bathing the Earth, not quite uniformly, but pretty uniformly in the electromagnetic radiation. Sorry about these jumps in the tape. We did a lot of hacking around to extract this from the 15-minute videotape. So here it is orbiting up there. The scale, radius of curvature of the Earth is all out of scale in this film. That's just the front of the GPS unit they're really marketing. Here's the constellation, and you see the satellites orbiting. I don't know, it doesn't look like the artists let the Earth rotate, but they should have. And now it's kind of slowed down here. And so a lot of satellites up there, and I haven't counted to see whether they got all 24 represented there, but that's the constellation. It's a bird cage around the Earth. It's a really neat thing. That's to scale, I believe. It doesn't look like my scale. But let me turn this off. Figure out where I am here. Yeah. Okay, here's another view taken from the artist drawing in the Scientific American. Shows the front of the satellite a little better. Down here are the radio frequency transmitters. There are the solar panels. The first panels had some vacant real estate in them to allow for the fact that later GPS units might need more power, and that's what happened. The later satellites use more power, and they have the solar panels totally filled in. This part up here is a piggyback unit called a bang meter. There's some of the other things up there, which are used to detect nuclear explosions on the surface of the Earth, in the atmosphere, or in space. So these GPS satellites do one other job as well, but that's not important for our purposes here today. Okay. I'm going to slide over this transparency rather quickly. If the Earth were a perfect sphere, then 6 numbers, 6 parameters would determine its orbit for all time. 5 determine the orbit, and the 6th one, a time when it's closest to the Earth, would determine where in the orbit. You'd like to have circular orbits, but you never get it perfect, and so you always have an ellipse. The long axis of the ellipse is called a major axis, and half of that is called A. If it was a circle, A would be the radius. So that's one parameter. A parameter which measures how much the major and minor axis differ, called the eccentricity, is controlled very well when they launch, or they correct for launch errors. They keep the eccentricity less than 2% in the system. There's the inclination I explained already, 55 degrees. The nodal thing tells you which plane you're talking about. So divide 360 degrees by 6 planes, and you figure the difference in omega, another angle between the several planes. Where the closest point to the Earth of the ellipse is called the perigee, point closest to the Earth, farthest away is the apogee. That's measured by another angle, and then when the satellite's at perigee. So the 6 numbers, that's the only important thing. Determine, and 5 determine the orbit, and the 6th where you are in the orbit. And if the Earth was perfectly spherical, measure them once, it'd be true for all time. And in fact, various things happen, and I'm going to go over this rather fast too. The Earth's equatorial bulge, the fact that it's fatter around the equator, causes this plane to rotate about 14 degrees a year, doesn't really stay fixed. And there are other effects due to the Earth, planets, moon, and so forth. And so the orbital parameters are measured by ground stations, and then the measurements are sent up to the satellites, which tell the receiver units what the orbits are. And rather than describing the orbits, they give the new parameters, the new Keplerian parameters, and also the rate of change of those and so forth. The ground stations also measure the clock drifts, and those are sent up, and the satellites tell you how much the clock is drifting and so forth. And rarely, but sometimes, they have to use satellite thrusters to correct the orbits, but there's only a certain amount of rocket fuel they carry up there, so they don't like to do orbit corrections if they can avoid it. Now, here's something surprising, and that's that all the GPS satellites emit the same frequencies. There's actually two frequencies. You might think, well, the easiest way to tell the 24 satellites, the 21 operating ones apart, would be to have each one emitting a different frequency, like 21 different radio stations. If you had that, that would be nice. Here's one tuning fork, another one. And you can tell there's two things there, and if you wanted to, you could figure out which was which. But it's not that way for the GPS system. All 21 satellites are singing the same note, and you can't tell them apart from just listening to that note. So, what's going on here? The two notes are called the L1 band that each one emits, the L1 band and the L2 band. Okay, the L1 band is 1,575 megahertz, corresponding to a wavelength of 19 centimeters. That's called a carrier. And the other one is somewhat lower frequency, a 24.4 centimeter wavelength. So think of the L1 band, 19 centimeters. So think of there's a ruler called a carrier wave, which is 19 centimeters. That's an important number, which I'll comment upon briefly at the end if I have time. This signal, this carrier, is coded. There's information put on it. It's called a clear or acquisition code, or C/A, by something called a 1023-bit pseudo-random number code, a PRN code. It also is coded with a second thing called the precision code, which is a 6 million-bit pseudo-random number code, which can be encrypted, in which case it's called the Y code. Now, coding and encryption are not the same thing, even though those words are used as synonyms in the popular language. Coding means information. Encryption means a key. It's scrambled information, which you need a key to decode it. The L2 band has the P code on it, and it can be encrypted as well. You can think of clear also as crude. So crude and precise are good ways to remember it as well. These codes enable the users to distinguish the satellites, to tell them apart from one another, and to find the timing marks, the clicks of the clock, so to speak. The use of these two frequencies allows much greater corrections for the variable ionospheric effects. There is weather in the ionosphere, so you can't measure it once and then correct for it for all time. And so the two frequencies are used to remove the ionospheric propagation effects due to variations which are not predictable. So that's why there's two. Okay. Okay. There's more to it than that, though. Let's first just do this part here. On the CA code, the accuracy can be deliberately degraded by something called selective availability. So when S/A is on, the clock signal is deliberately dithered, both over short terms and long terms. So the system spoils the accuracy that I get. I don't get the accuracy from my $300 that the system has, because they're deliberately putting dithers in the clock signals. The P code doesn't have that, but it's available only to authorized users, which means military users, not even commercial aviation. I won't have time to talk about the power, but it's equivalent to a 15-watt bulb in San Francisco, a Christmas tree light bulb, as viewed from Chicago, if you've got up on a very tall version of the Sears Tower. Very weak levels, so these signals are easily jammed and they don't penetrate buildings, couldn't use it in this room and so forth. So that's the way the satellites are told apart, because there's certain coded information put on the same carrier, on the carriers. One code is much longer than the other. It makes it more difficult to jam and so forth, but I won't get into that now. I can't resist telling you how this stuff is coded because it's really cute. You've probably heard of AM modulation, amplitude modulation, and frequency modulation, FM. Well, this is done by phase coding. So the pseudo-random number codes are just binary digit sequences, some ones and some zeros in some order. It actually repeats eventually, so it's not truly random. And the one code repeats after 1023 steps, the other after 6 million steps. So it's a string of zeros and ones, of binary digits. Here's the carrier, and change these zeros to -1. That's equivalently good way of viewing it. So here it's a 1. Here's a 0 represented by a -1. Here's two ones in a row. So it's a 1 and a 1. And here's another 0 or a -1. So multiply the binary sequence here by the carrier wave. So what happens is that the carrier wave, when it reaches a boundary between 0 and 1, it's flipped in phase 180 degrees. Instead of going up, it starts going down. It's the green thing. At the next boundary, the phase is flipped again. Now there's nothing in the middle here. It's a couple ones in a row or something. So it does 2 cycles. And then hits another boundary. You either went from 0 to 1 or 1 to 0. And it flips again. It's easy to pick out these points. That's phase coding. You don't have to do great precision. It's easy to pick that out with electronics. And so that's how you decode or you get the information that's phase coded. It's a very robust way of coding. Okay. The way the receiver, the user, does the job is to generate in his or her receiver a pseudo-random number code that corresponds to a given satellite, and then tries to match it to the signal received from that satellite. So here's the generated one, here's the received one, and you slide this in time to make them overlap, and that's how you figure out the time delay. That gives you the pseudo range. It's the same as, but I won't really do it in detail here. So the way you do this is called calculating an autocorrelation function. So here it is a pseudo-random code, and here's the same one. And they arrive, one is generated by this unit, the other is received by it from the satellite upstairs. And as you slide this over this, at some point, bingo, they line up at the right time delay. And so say, aha, that's the delta t, the time difference of arrival. Because, that's how you measure it. And you do that for the 4 satellites, and then you're off in business. So that's called an autocorrelation function. You compare a signal to a carbon copy of itself. So that generates the pseudo-random codes for all of the satellites in the system. Okay. Now, what's the accuracy of the GPS system? Well, there's no one number, and one of the confusing things is you hear many different numbers. But that's because people are talking about different measures of accuracy. Absolute accuracy means where you are with respect to some fixed coordinate system. When you're using the clear or the acquisition code, which is what the cheapest receivers used, and they're degraded by having a selective availability on, the sort of average accuracy is 165 feet, but there are error bars on it. It can be as low as this, which is about 50 feet, but you only get that about 5% of the time, and it can be much worse, and the other end of this is off scale here. It could be quite a bit further out here, probably a little bit beyond that. It could be more than 300 feet inaccurate. If the selective availability were turned off, on the average you'd have 50 feet, sometimes as bad as 100, sometimes as good as 12. but only 5% of the time that good. The military available precision code is on the average 25 feet and never worse than 35 or so. If all you want to know is the difference between the distance between two objects, that's called a differential measurement. You don't ask where they are in absolute space, but what's the difference, then with or without the selective availability turned on, it doesn't matter. You can get 8 feet on the average, and sometimes much better. And by techniques which use other things like long-term averaging and whatnot, you can get down to fractions of an inch. And some methods use techniques which I'll just touch upon briefly here, which get you down to millimeter in differential measurements. These kinds of differential things were never really thought of, dreamed of when the initial system was defined. And so their use, which have become already standard in survey, are defeating the selective availability. And there's a big issue going on about turning that off because of the importance of the greater accuracy, the more than this shows about a factor of 3 accuracy, sometimes a factor of 5, that commercial users would get, and civilian aviation would like that factor of 3 as well. Here's an error budget for the GPS system where the errors come from. The satellite clocks contribute a range error of about 5 feet. Our inability to know, to measure, to maintain the satellite orbits gives us another 8 feet. The uncertainties in the ionosphere and the variations in it give another 16 feet error, and the atmosphere, lower atmosphere, 1.5 feet. The receivers are incredibly good. Multipath means reflection from the Earth or buildings and whatnot. They're negligible. You can see the biggie here, which is way off scale. Here's 20, 5 times higher, is the error put in by the selective availability. Every time someone buys a GPS unit, there's another vote for turning off the selective availability. I'm told that an obscure piece of the defense budget that was signed by President Clinton recently says that the SA will be turned off on May 1, but there's a loophole that gives the Department of Defense more time to operate it if they claim they're working on countermeasures and so forth and so on. So it'll be turned off, but I don't know exactly when. Okay, the last thing I want to say is what differential GPS is. Suppose I place a standard receiver at the end of the runway at O'Hare Airport. Okay, and I can have a person there or a machine which is reading where the receiver says the end of O'Hare Airport is. You're coming in on your plane with a GPS receiver, and I send you a radio frequency signal saying the GPS unit at the end of the runway where I'm located is giving an error in the X, Y, and Z directions of a certain amount. So I tell you how much it's wrong, and that includes the error that the selective availability is deliberately putting in. You can use that to correct the information in your receiver, provided you're using the same 4 satellites. And so that's the differential technique. So you get around that error by basically subtracting it out, and that, as I said, doesn't matter whether the SA is on or off. In fact, there are commercial companies now which provide that to you, broadcast the information down from satellites in space. So it's just an open market. Having this has made new businesses possible. There are numerous ways to transmit these corrections. By radio waves is the most common way. A second, or you need another communication link. You could do it with carrier pigeons, but the trouble is there aren't any carrier pigeons left, or the market for those is rather small. One other technique of improving the accuracy, and this is what the surveyors use, and people studying continental drift, the kinds of things Professor Chang was talking about, make good use of this as well, and that's that you use the fact you've got a ruler in your system that's very well maintained, very precise, that's marked every 19 centimeters. Okay? So if you could make use of that ruler, and you can interpolate between the marks on a ruler, you can do better than 19 centimeters, and that's exploited in a number of the differential applications, and it's the analog of counting fringes in optical interference patterns, called interferometry. You can measure very small distances if you can get interference patterns, and you don't make any use of the coded information on the carrier. It doesn't matter at all. It could be just an uncoded wave. You're using the carrier, and that's used in surveying, and you get greater accuracy if you can do long-term averaging. It's also used to monitor the orientation very precisely of spacecraft, so you know exactly how it's oriented. Certain tests of general relativity are done that way. And it's the basis of something called a Stanford bubble, which will become the standard way for aircraft landing at commercial airports. It's a technique invented as a study problem, a homework, take-home exercise in one of the graduate courses at Stanford University, and some graduate students came up with this. I won't have time to explain it. There's a couple slides in your handout, but I'll just show you one result of that and then call it a day here. This was a test done by using a Boeing 737 loaned to the effort, including a pilot by United Aircraft. And so the landings were done totally instrumented. The pilot was sitting on his hands, no touching the controls. It's a GPS unit with the augmentation called the Stanford bubble, which is not a GPS unit at the end of the runway, but a couple very low power beacons which are picked up by additional antennas on the bottom of the aircraft, which basically give it one initial fix, and then it counts wavelengths coming in, counts fringes the rest of the way. Okay, here's the aim point, and here's a box which includes 95% of the touchdowns. The aircraft is coming in from the left here, and here is position in 1,000 feet. And so here are the landing positions. Now, the first thing you say, they always miss the aim point. And so when I saw this presentation by one of the Stanford students who at that time already had his PhD, and they're already in business for themselves in Silicon Valley, I should say, we all said, well, why did you always miss? Well, it turns out that this is the normal aim point, but when a plane is landing at the last minute, they do a flare. And so the flare was not shown in this. So when the plane gets very close to the ground, there's a flare, which is determined just by the height above the ground. So that's the reason there's this bias. The center of this really should be called the aim point. Imagine 747, pilot sitting on his hands. It's landing itself. Pretty good. There was one case in which the system, in a sense, malfunctioned, and they had to do a wave off. Now, what about that? You say that's not good enough. It's actually easy to get the accuracy. The hard part is reliability. They've got to demonstrate 1 in a million or 1 in a billion rate of failures. Accuracy is not the problem, it's reliability. Well, that one wave off was the fact that the system detected that some GPS signal had an anomaly in it. Just like there are leap seconds. GPS clocks have to be corrected once in a while until the little jink in it. The system detected that one of the GPS clocks that was being used had a jink, the carrier wave had a jink in it. It said, something's funny going on here. I'm not going to land this plane. So the plane, the autopilot just took off again. So, in a sense, that wave off was a success of the system. There was a thing called a microwave landing system, which was being developed for about 20 years. There were a few airports in the world putting it to use. Probably another $10, $15 billion, or maybe $10 billion been invested in that over a 20-year period. And it's being thrown overboard because this technology is far superior to that. Anyway, that's the end of my story. I ran a little bit longer than I intended, but thank you for your attention. I'm glad to answer the questions.
Very much all for coming once again to our program. Let me remind you that there's going to be a tour showing how to use a handheld GPS device, which will start outside in the lobby. And I hope to see lots of you here 4 weeks from now. Thanks very much. Thanks.